Thank you very much for the introduction. So today I will try to summarize the results of the collaboration of the Heckel and Lemesco group on the orbital angular momentum-enabled Ro-Vibrational Spectroscopy of molecules. There are a lot of like people involved, but first I have to start with the beginning of why we actually want to do this. So the reason is that, well, it's well known that if you have like a gas of molecules, and then on this you shine some kind of laser in the mid-infrared, you actually excite a lot of rotations and vibrations, and there are already books that write how things work. But then people just said, okay, we have now these nice beams that instead are not like completely like plane waves, but what they have is that along the azimuthal direction, they have a phase. And people have shown that these actually contain additional angular momenta, the orbital angular momentum of the beam associated with this phase. And then this might introduce new transitions, and we can write some new chapter in these books. We are not the first to try to address this problem. There are people have tried with point charge models to address this, but these tend to be non-versatile, have a lot of ad hoc assumptions, and they're complicated. You cannot do this for every molecule. So our approach was to just, okay, let's do it systematically and start from the QED Hamiltonian, the powers in Auli, and then use image spherical charge densities that can rotate nicely, and we can actually like also take the limit of the point charge of a single point in space representing the molecule, which is like the far field approximation, while keeping the multiple moments constant. And from this we arrive to this, so I call it like Maslov Hamiltonian. This looks very complicated, but this has like extremely good properties. Why? Because it separates the interaction in three terms. First is the multiple moments measured in the reference frame of the molecule, and this accounts for the internal degree of freedoms and the transition multiple moments. The field comes completely parametrically in terms of its gradients. And we can use essentially any field we like, and then all the rotations and selection rules and whatever comes in the third term with all these nice D matrices. And my favorite quantum number in this expression is this M here, which actually counts how much orbital angular momentum is transferred from the beam to the molecule. And this enables new transitions that you won't find in books. So with this, we actually be able to characterize the selection rules. And first, I start like with something that is not very promising, maybe. So when we go to dipole approximation, what we see is that the spin of the light corresponding to its polarization is what is actually transferred to the internal rotation. And what the orbital angular momentum does is just forces the molecules to orbit the beam. So not so inspiring, but when we actually go to higher order of interactions, and we can do it for all orders, but let's say for the quadruple moment, what we can do is that we can transfer quanta from the orbital angular momentum of the beam to the internal rotation of the molecule. And this quanta is kind of like depend on this L, which for quadruple is 1, for octuple is 2, and so on. And our theory is kind of like can be used for experiments quite easily. So here, what we have done is like we simulated what would happen in a molecular chamber experiment. And look and behold, here the red line in the third plot here, I cannot point, unfortunately, is the new transition that we have. And the very good feature of this is that it's quite extensible, this framework. Now, after doing all this, what we went and do is like we tried to optimize the field. Why we did do that? Because we have a small problem. And if you do not see the small problem, it's here on the axis. You can see that the absorbance is 10⁻⁷. So why is that? There is a simple reason for this, and we need a little bit to get into the mathematics. So we take an arbitrary paraxial beam. We can split it in 4 components: the polarization, the electric field, the phase, and here somewhere is kind of like a dimensionless factor if you remove all the scalings. That is the shape of the beam. For all allowed quadruple transitions, we can form the matrix elements. So if after averaging, what we get is something like that scales with the amplitude of the electric field and the wave vector. But then if we actually go to the forbidden transitions, we get a term that we don't like, this one, which actually quantifies how much justified is our paraxial approximation, because it measures how big is the wavelength over the width of the beam. So that's actually like tanks the signal. And then there is this term that might help us. So the gradient of the field, which introduces after averaging this gradient factor here. But this is just the order of the beam. So so it's kind of like the GUI phase. Maybe you can experimentally know what this is. And what we need essentially is like very large. In order to compensate this, we need very large ordered Hermite Gaussian or Laguerre Gaussian modes, which are a little bit challenging. So what we can do to actually fix this problem is, first, we can go to strong focusing. Now this is like somewhere we're very much working on, or we can trap the thing. Why we can trap the thing? Here I have like, just except from a nice figure, what this actually shows you is the spatial distribution of this signal here. And while for Gaussian beam, we can also get some signal from these transitions. From the Laguerre Gaussian beam, we have a very strong signal close to the core. So maybe if we can put our particles there, we can get more strong spectroscopic signal. So this is more or less, there is a lot of work being there. I will not bore you with more details. As I now like switch gears, and I will go to an enantiomeric spectroscopy. So what chiral molecules are, it is already introduced. I will just say that why we need to separate and see what is left and right. A reason is here, for instance, that for methamphetamine, one of the components is actually nose deconjectant, the other is a drug. So you want to separate before taking either. Yeah? So the thing is that people actually have worked on this enantiomeric separation, and mostly they use the polarization of light, because differentially left and right-handed polarization propagates with different velocities on the molecules. But now people say, okay, now we have this nice orbital angular momentum. So maybe what we can do is to, and this produces these chiral phase surfaces. So what we can do is to just like make them interact with chiral molecules, and maybe these can be different than this. Of course, like rigorous theory on this didn't exist, but people actually have progressed and actually have shown that if this exists, the first term to look at is the, if you expand the matrix element, it will actually start being visible in the coupling of the electric dipole to electric quadrupole interactions. And then the question here that we can ask based on our Hamiltonian is, what transitions are allowed that have both dipole and quadrupole transitions? So we opened the book, find out all the states of the asymmetric top rotor that most of the this kind of chiral molecules are. And then what we found out is that all these transitions actually require that you have a 0 orbital momentum quantum transfer number. So you cannot transfer orbital angular momentum, at least in the case that you require some finite, some polarization. So in the paraxial approximation where the polarizations do not mix. But what we said is, okay, let's mix the polarizations by introducing a very large focusing of the beam. And then what we found is that, okay, without the focusing, nothing happens, as I have said. So there is no benefit from using a larger Gaussian beam. But with strong focusing, what we actually see is that the spectrum we get from the one enantiomer, it's different than the other by a rotation. So in experiment, maybe one can observe this for larger Gaussian beams. A little bit not satisfactory for people is that, okay, this is actually possible also to do it with a Gaussian beam, because the focal field that you generate when you do strong focusing is actually larger Gaussian, which is actually funny. So with this, I would like to summarize our results. So in summary, we have derived the very general Hamiltonian we can use for spectroscopy, for a vibrational spectroscopy of molecules, and we can actually try to probe all different kind of like spectroscopic schemes and understand what is the role of the orbital angular momentum in this kind of setups. Thank you for your attention.
Nice talk, thank you. So you kind of a little bit pessimistic conclusion, right, Joe? Is there something optimistic about Laguerre Gaussian beams?
About Laguerre Gaussian beams, so the thing with Laguerre Gaussian beams is actually that this factor here, that if we go like, for instance, to Zeilinger, yeah, anyway. So this P plus M here, so this amplification that you get from gradient, Zeilinger has optical vortices of like thousands of quanta. And it seems that, and of course, what happens is that this can compensate the non-paraxiality factor you need. So for optical transitions,
I don't know what non-paraxial.
yeah, so non-paraxial is like if you are going like very, very strong. So the idea is that there is the wavelength, the light, and the width of the beam. When you actually focus very, very strongly, what happens is that there is coupling of polarization with the of polarization and the structure of the beam, and this creates new terms in the Maxwell equation, and you cannot use paraxial approximation anymore. You need to get focal fields, and so people do not, so experimentalists do not really like working in this regime. This is the regime of high numerical apertures, actually. So people are pushing to this. But yeah, so in this kind of like case, one can go and do orbital angular momentum spectroscopy very well. And then, of course, the other thing is kind of like that if you have large resolution of where your particles are, this is always good, because the fact that here they separate from Gaussian beams means that you don't, that if you actually know where the molecule is, you can separate between the signals and don't have things that drown you.
Thank you.
More questions? If no, let's thank Georgios and all the speakers in the first morning session.